Alright, in this video we are going to discuss uniform flow. Uniform flow, as we know, is one where the depth of flow at a section is exactly equal to the depth of flow at another section. This depth of flow is also called the uniform flow depth, denoted by y0 or yn. And we also know that the velocities at these two sections are also equal. Uniform flow almost never exists in reality, but we still need to study it, reason being that it serves as a benchmark to study more complex problems which we'll be looking at later on in this course. Also, if you are to design a channel to convey a certain amount of discharge, then uniform flow concepts would help us to determine what should be the minimum cross-sectional area of that channel. Now the discharge, as I mentioned, the discharge Q may be determined either by demands or from hydrologic analysis. Let's say we are to design a channel beside a road network so that the channel conveys all the drainage from all these overland areas, all these drainages eventually drain into this channel. Then the channel should be effectively conveying all the water in order to prevent flooding in the surrounding roads. Or similarly, if you have an irrigation channel, the discharge may be known to you because a certain amount of water is necessary to be provided for irrigation purposes. Now these different channel cross sections that you see here, they are constrained by how much area or land is available and what are the terrain characteristics, what are the soil characteristics. So these are determined from beforehand. And the slope of the channel, so if you have a vertical here, there's a certain angle, this angle theta is also predetermined because of the terrain characteristics. And there can be different materials used in lining these channels. We see an unlined channel here, and we see a lined concrete channel in this figure here. All right. In each of these cases, so we have Q, the cross-sectional area, the bed slope, these are all predetermined, and therefore we need to find the normal depth which will convey this discharge through a channel. And uniform flow, like I mentioned before, it never exists or it seldom exists in reality. However, it can exist in a combination with other types of flows. Like for example, we see here there's a channel which takes off from a reservoir, and right at the point where it is taking off, one can encounter rapidly varying flows. This is followed by gradually varied flow, and eventually the channel has a uniform flow depth, and eventually the channel may fall, there's a drop or fall, and eventually the channel drains into a lake. So here we see uniform flow in conjunction with other types of flows. And in this section we see another example where the channel bed slope changes from a mild slope, it becomes a steeper slope. And here also you may have uniform flow in reach 1 and in reach 2, but in between those two one may encounter non-uniform flow. Therefore we need to study uniform flow, and in order to study uniform flow, let us consider the forces. So if we consider a control volume within a channel such as this, along the sides of this control volume you have pressure forces. So the pressure at section 1, which is hydrostatic, pressure at section 2 is hydrostatic, and because the depths are equal, the relationship between P1 and P2 for uniform flow would be P1 is exactly equal to P2. The weight of the volume of water contained within this control volume is W, which is given by gamma, which is a specific weight, rho times G times the area times the length of the channel. And a certain component of that weight acts along the direction of flow, which is given by gamma AL sine theta. There is also another force which is acting on the control volume, and that's the force of resistance, the frictional resistance, whose shear stress is given by tau naught. And here the water surface elevation is also shown in the cross section. The cross section can be anything. If we write the momentum balance equation, then we have summation of all the forces equal to 0. Reason being, the velocity at section 1 is equal to velocity at section 2, hence there is no acceleration. And we have just shown that the pressure forces are also equal. So this leads us to a relationship between the frictional forces and the weight component. So if I denote the slope sine theta by the bed slope S naught, then gamma AL S naught is the component of the weight acting along the direction of flow, and tau naught times P times L is the total frictional resistance. So this is my frictional resistance FF. P times L is essentially the area along which the shear stress is working, where P, as we know, is the wetted perimeter, and L is the length of the channel. If we equate these two, then we have essentially derived a relationship between shear stress and the slope. So we know that the hydraulic radius is given by area divided by the wetted perimeter. So from this relationship, we have tau naught is equal to gamma times R times S naught. So this is the momentum equation for uniform flow. In the next video, we'll discuss some cases and how we see how these frictional resistance laws are acting for uniform flow. So see you.